And the last time we stopped in the term of sporadic, and we saw that if the roots of my differential polynomial are greater than the spectral norm of then the operator norm of the derivation, then in that case, the spectral norm of nabla E are exactly equal to the absolute value of the roots of the commutative polynomial. Now today we will see the version of Hansen lemma for differential polynomial, and for which condition we can apply we can decompose the principle of Hansen lemma for commutative polynomial is to reduce to the residue fields, and if there is roots there, then it means that we can if we can decompose in the residue field, then it means that we can decompose in the big field. The big field. The question for differential polynomial, it's quite different because we have because it's not commutative, and it cannot. There is some supplementary condition that we need to have this result. Then before talking about Hansen lemma, I need to give this definition. Then if we have a commutative polynomial, then we denote by WR, and we have R a positive real number, then we denote by WR just the number of roots that I have, their absolute value exactly equal to R. We know that if we are in commutative polynomial, then it is evident that if we multiply two polynomials, then we will just here as a remark. Then for commutative polynomial, if we have then it's obvious that it's something like that, because we will add the other roots of the other polynomial. However, the question now and here I just give the definition using the absolute value of the roots, but there is a definition using the Newton polygon and the length of the slope that we give you this same number, and we can got this number from the coefficient of the polynomial. That's why we can define, if we consider a differential polynomial, then we will define this value just to be the same value if we consider it as a commutative polynomial. And in that case, if we have the roots, the absolute value of the roots of two polynomial greater than and this value I will define it especially only for R who are strictly bigger than the norm of D. And in that case, and if we consider P, D, Q, T, D, in that case, we also have This just mean, even if it's not commutative, when I will develop my my polynomial PD multiplying by QD, the root will change, but their absolute value, they will not change, because this, I will just give an example. For example, for degree 2. Then let's take, for example, d equal d over dt, and we consider omega equal h, the simplest case. This just means that the absolute value of t is equal to 1. For example, if we consider, just give us example of degree 1, not d. Here, just in that case, we have the absolute value of t is exactly 1 over 1, then in that case it's equal to 1. Then we just need to provide roots with absolute value strictly greater than 1. For example, here we will assume that the residue characteristic is equal to k, is equal to p. In that case, the absolute value of p is less than 1, which means that this one is greater than 1. And take another one with different, with different roots, but not with the same absolute value, p minus 1 and t squared. We put here t squared. Then we will develop as in the usual case, and in that case, just we have something. Here we just have something to do. An absolute value of and this is exactly C1 fuzzy. That's why it doesn't change the absolute value of the coefficient in some sense. Even with that's why when we would look for the roots of this new polynomial, we'll recover the same absolute value of the roots, but they are not the same. The roots, they are not the same, but with the same absolute value. And that's why we have this result. Yeah. Now, Hansel lemma. The theorem. There is different form of Hansel lemma. The initial one is the one that looks like as in the case of commutative polynomial. And however, for that, we need to impose this part. And then we need this condition. Otherwise, it will not work for our. This condition permits that the derivative can be defined on the residue field. before saying that, prefer to make some notation before stating the theorem. Because if we have a derivative that satisfies this results, then we can extend, then we can define the reduction of my differential polynomial. And we have then in that case, we can define d tilde as the endomorphism of this. This is just, if you have an element here, just take the this and use. To a natural map from omega d to omega tilde d tilde. However, in this situation, everything is well behaving. However, in the special case, for example, if just in that case, if you have that, then this, what does it mean, such up? If we have a polynomial here, then we have, then if this is the reduction mark, in that case, just the point is when we will be in the residue, consider the residue, this this ring, then if the operator norm of D is strictly less than 1, then in that case, this not differential twisted polynomial will be commutative, because if we take an element here, oh, sorry, I make a mistake here. Here is omega, the ring of integers. The elements have the norm equal to 1. Then this is this one, and which means that it is something like D, and here we have D plus. And this element, since the operator norm is strictly less than 1, then we will get this. Strictly less than A, which is equal to 1 in that case. And this means that the dA in this field is exactly equal to 0. And that's why we will have equal to this, which means that we will obtain a commutative polynomial. That's why, then if we have a polynomial in the beginning and in the residual field we have this commutative, everything is behaving well, we will get, if we get a decomposition, then we can lift this decomposition, but we can lift it in 2 ways. If we consider it's depend on the roots, then we can put the root in the right side or in the, not exactly the root, with the same absolute value, that's what I mean, in the right side or in the left side. That's why we have the Hansel lemma left and Hansel lemma right. Which means, in some sense, if the commutative polynomial, but we need some, if the commutative polynomial can split, then so is for the differential polynomial. However, this condition means in some sense that the roots are strictly less than, strictly greater than the operator norm of D. However, here, for example, if we got that only in the derivation is equal to 0 in when we reduce this derivation equal to 0, especially in only in the case where the norm of the derivation is strictly less than 1. Otherwise, it's not the case. It can be the case, but it's a very specific case that I will give an example, for example, after. Assume. This is just an example, but it can be equal to 0. Assume that this is then if P is equal to some with then we can use, we will see after, we can use the Hansel lemma by reducing to the residual field when in some sense the polynomial is separable or it's totally tamely ramified. Otherwise we cannot cannot decompose, and that is the problem, especially in the p-adic case. For example, if the residue characteristic is equal to 0, we have two situations: if the extension is unramified, or it's temporally ramified. We don't have other condition. However, in the p-adic case, there is such a situation that make things more complicated for where the residual characteristic is equal to p. And we will see after, also for other points. Then exists or just Q1 D respectively. Then such that we have Q1 residue is equal to Q2 Y D, and we have then PD can be decomposed in that way. Or the other way, or which means we can lift the roots of R, and we can choose if we lift the roots of R in the left or in the right. And this is important for after to use it to decompose a differential module into a direct sum. Because we know if we can decompose the differential module, we can have an exact sequence, but can we deduce that this exact can we obtain a direct sum? That is what we will see in the next. And this is in some sense when we impose that the derivation is trivial, and in some sense that it just means that the roots are strictly greater than the norm of the derivation. Then, however, this is not necessary. For example, if, and from this theorem, we can deduce a general result, and we can choose any derivation. and we will just get this result from the absolute value of the roots. And this is the theorem that we can obtain. This is a corollary. Then can assume that we can have this. And let R then if is less than R, and respectively. It's just here. It's the that. This is almost the result that we will use later. Then omega. Here's another way where they don't use the absolute value, but they use the slopes of the Newton polygon associated to the polynomial, which is a combinatorial object that can give you all the absolute value of the roots of the polynomial. The point that we need to be careful is if, for example, we have a root that its absolute value is less than d, then when we will decompose, compare, it will not be the same. It will be just less than r, for example. Here, if it is less than r, then if ZE0 is less than r, and especially if it is less than the absolute value of t, then we will find another root which is not exactly the same as the initial one. It can change. However, for the other one, they don't change. They remain the same, because when we change them with the derivation, the absolute value, the roots of the absolute value will not change. And for the bigger one, they will remain the same. And especially if we know that all the roots are greater than d, then it's okay. Then we will have the equality. If moreover, then we will have the inequality for all. Now let's just make an example. I was sure to do it before, but just example. We have a case, a special case. If we consider omega of, if we trivially and we consider omega to be omega d to be these fields, these differential fields, this is a specific one because we here, for example, we have the derivative, the absolute value of the derivative equal to 1, but the derivative on the residue field is 0, because we know that the residue field here of omega is exactly equal to the residue fields to k, and since it is the trivial trivial absolute value in k, then it's exactly equal to k. And in that case, the derivative t over dt, when it acts on a non-formal power series, just for example, if we have t power e, then d over dt of te is just e multiplying. Just let me just put it here. It's exactly something like that, which means that the image of all these elements on the residue field will be equal to 0. So this is this is mean that it would just be something like, if I have an element here, the A will be 0. Because all the absolute value of t are less than 1, and hence their image is less than 1, then it means it's 0 on the non-constant element. And we know that derivation is 0 on the constant element, which means that in the residue field is equal to 0. And that's why, for example, in that case, we can apply directly the Hansel lemma without any problem. However, in more general situation, it's better to use the corollary instead of the big theorem, the first version of the theorem. Now we can announce the important theorem that is as follows: decomposition theorem. But it's a theorem that it's holds for theorem. Here, just found it. Otherwise, it doesn't mean anything. Then this decomposition is unique as I will exist. Yeah. The spectral norm of any any subportion of MS is it's exactly equal to S and every subportion. Then in that case, the subportion of M0 are, we don't know what they are exactly. We just know that they are less or equal to the norm of the derivation. Then we will prove this theorem. Then we will induct in the dimension of V dimension of M. Then since we are working on a fields, then there exists a cyclic basis. Then we can write our differential module as by using a differential polynomial. 10. Let then in the case if all the roots are less than the norm of t, then we just set if when the biggest one is less or equal to d, then we just set m0 equal to m. We cannot decompose it more than that. And in that case, each quotient will each subquotient of that will probably have the spectral norm of the connection strictly less or equal to the norm of the derivative. Because if we decompose, we cannot have something bigger because what now if now this is B. Then we will got then that E here by using the corollary that we such that omega r of q d is exactly equal to omega r of pd, which means the same number, and they are also equal to the degree of q, which means that all the roots of q as a commutative polynomial, and this is the same of this means that we have an exact sequence for sure we have here is equal to 0. then just just put it, just it's the same if I just add prime everywhere. And then we know, since then we claim that in that case M nabla is a direct sum of V plus, and here we set just this one. Just for the hypothesis of yes, just for the hypothesis of the induction, it's easy just to see that for dimension one it's okay. And here, then why we have this direct sum? Then the first part is this is equal to 0. Why? Because both of the two, we can see them as a part of M, and for V, we know it has a dimension less than M, and even without using that, by using, we know that all the roots are greater than T, and we know that all the roots are equal to R, and we know that all the roots of W prime are strictly less than R, and this means that we cannot, if there is a sub non-trivial sub differential module, this means that how to say it? It means that in one part you will have roots, only roots that they are less, and in the same time, or only the root that they are exactly equal, which is and for the, then we know that then it is a direct sum. Then we know that it is a submodule, and we know that this one is exactly equal to the degree of Q, and this one is probably equal to the degree of P minus the degree of Q, and which means that all this because they have the same dimension, they should be equal. It's equal to the dimension of them, which means that we must have this is the, and that's why we have then by induction that probably the other one, since it is the dimension is less than omega y, then it's, the first one is less, dimension is less than, it satisfied the condition of the theorem. The other one also satisfied, then we can do that by induction, and we got all our decomposition. Then the good part is the case the problem when we are working with the residual characteristics equal to P. In V0, there is some submodule that they will have the radius of convergence less than the radius of the points. However, for less than the point and greater than omega, the radius of the point. And we don't know about that. We will see. Maybe I hope that we can do it this Thursday. For that, we use other technique. We use the Frobenius to make, for example, the norm of the derivation smaller, and after that we can decompose. However, for the case where the residual characteristic is equal to 0, the good point is the norm. The norm of the derivation is equal to the spectral norm of the derivation, which means that if the V0 will correspond exactly to the differential module who has the spectral radius of convergence exactly equal to the radius of the points. I will not have the problem with the gap between. We don't need anything. This is in some sense in the residual when the residual characteristic is different from is equal to 0. There is no notion of Frobenius. Frobenius is just using the power by P, and in the other case we have that, and we use that to resolve in some sense our problems. Then, as a consequence of this theorem, I just forgot to just here. Then I said just H0 equal.
老师、同学您好，请在教学楼入口或进入教室后主动扫纸巾码，全程佩戴口罩。
This just means that we will measure the default or surjectivity. And in a special case, for example, if the radii are small, we know that our connection is injective. However, what we can say about the surjectivity? The good point is when the radii are small, then we can deduce that the co-kernel of. Before that, I just need to use another result for. I forget. here the absolute value is not important. It's a result from algebra. It doesn't depend on any absolute value. And here just we will use the unit extension, which is the same as the set of something here. With the quotient of such relationship. For example, if the direct sum will correspond to 0 in that case, and we will use that. Sorry, it's not on. Which means that if this connection is not surjective, that there exists, they can be, if we have an exact sequence, it will not be automatically a direct sum. It can be other thing. This just means that the M0 of Nabla, the M0 here is equal to, it doesn't exist in, this one doesn't exist. I'm just considering as a differential module just on without this part. And in that case, yeah, this is overviews for this one. We know that this is equal to 0. However, it's also surjective. Then in that case, the connection is a bijection between the two. And in that case, we use this isomorphism. We know that this is just like for, this is exactly, so here is omega. And a connection here that it's like something that we had just to and in that case just mean that h1 of m is exactly the extension, the unit extension of omega m. Then we need to prove if we have an exact sequence like that, then in some sense, since omega will probably decompose, something like that. Then probably, then we should have and for dimension reason, then we should have and omega should be a quotient of omega 0. That's why. Otherwise, if we take the Gaussian, omega will have, we know that omega with d is something that I have spectrally equal to the strictly less than d. Then that's why it cannot be the case, but it must be equal. And for this reason, then this mean, then omega over m is isomorphic to omega 0, and in that sense, it's isomorphic to omega, and that's why we should prove that we have the direct zone, and that's why and it is isomorphic to F1, F2. F1 here is equal to the injection, and F2 here is equal to the projection. Otherwise, it doesn't make sense. Then we don't have too much time to prove the rest of the other results. The point is that, for example, if we can have, for example, we have two roots that they have the same absolute value. However, they are not that close. For example, the difference between the two is less than 1. In that case, we cannot not do anything. Otherwise, if they are a little, not far, it's not the right word, but not that close, then we can, by using Taimni ramification, Taimni ramification extension of the omega, for example, then in that case, we can also decompose our differential model with respect to this, and this by using the Hensel lemma, because when we will reduce, when we will reduce to the residual field, we will manage to separate these roots, not exactly in some way. We will manage to separate this root, and we can lift this decomposition on our fields. But we need that it's crucial to use the extension. It's not on the bus fields. We just define the notion of, in some sense, definition. And this just permit to refine the part of the decomposition that have the smaller RD, not the other part. For the other part, we can see that we can, but however, we need first to use the push forward of the Frobenius to make the radius smaller, and after that, we can use this theorem to decompose more and more. I will just give the definition. And especially this is also for example, maybe I will just explain, and for next time I will give the definition. We just explain in some sense, because we will not talk for the moment. We will not talk about residual characteristic equal to P, just with the residual characteristic equal to 0. And for example, if we know that each extension of any extension of K, then it should be equal to something like that. And we know here for in that case, the extension is not ramified. However, it's Taimni ramified. Then the good point is that even if I cannot decompose, for example, the point is that if I have this, just a simple example. Then as the roots of this associated to this polynomial in a timely ramified extension is maybe 3, so it's better to see. Then the roots are T where just we have this is equal to 0, which means just the generator of these are generators, which just means that we have then in that case, we can decompose our differential module in 3 parts, because if we take the instead of putting something like that, just consider this polynomial, and after that we can go back no, just show it later. The idea is to normalize the roots, and after that we will go different one, and we can separate them in the residue fields, and after that we can lift this decomposition and got a final decomposition. The next time we will see that in more detail, and especially here we have the good point is because we have in moderate extension, this is exactly equal to 1. This is a good point. That's why we can do it. And in that case, we can decompose our differential module in 3 parts. And we can stop here, and the next time we will see the more decomposition. Do you have any question?